Humans are a young species. There are other organisms that have evolved strategies to solving problems that we also have. So thinking about how sea creatures can change their color in interesting ways to control sunlight, or how certain decapods can change the pigmentation in their skin to control heat flows, or even how mammals have a system of pipes that we flow blood through to control heat regulation. These are very relevant solutions to some of our own really important energy challenges today. So I am originally from an architecture and design background and have somehow landed in this sort of materials science world. I am interested in fish and mammal inspired solutions to zero energy buildings and slide mold inspired solutions for resilient city design. And so pulling from the natural world to see if there's any kind of interesting insight that we can pull to address some really important energy and resiliency and climate challenges today. Something like 1/3 of all the energy we consume around the world is consumed indoors. A significant fraction of the energy we consume today is going into heating, cooling, and lighting habitable spaces. And the way we do it is largely inefficient. We have static structures that do not adaptively respond to changing climate, changing need, changing weather. And so the way we maintain a constant desirable temperature is through very bulky, very oversized, often very expensive, very energy intensive, active, the guts of a building really. And the proposal here is, what if we take a page out of biology's book where a lot of the climate control functionality doesn't only happen in the guts, but is actually displaced outward to the skin, the first line of defense. What if we can do a lot of the adaptive control right at the skin of the building in such a way as to drastically reduce how much energy we ask our heaters, coolers, and lighting systems to expend? We use a very simple architecture, a very simple system. If you think about what a window is today, a window is pieces of glass separated by gases. And all we're saying is, let's keep that structure. It's a really tried and tested structure. But let's be a little bit more creative with the types of fluids that we allow and move around within that cavity, and the types of designs of the sort of glass surfaces and their interactions. And so if you have this effectively container that can be filled with a fluid, a gas, a liquid, different types of liquids at different times, as simple as that might be as a building block, a container with a liquid, the richness in terms of the design options is remarkable. You really have access to a design library simply by moving different liquids into and out of cavities at different times that allows control of almost any really fundamental optical or thermal property that you may want to control in the context of a building. We have models that demonstrate if some of these systems were to be feasibly scaled up, we could be saving building energy by 25%, 35%, 45%, which makes a serious dent in global energy and global CO2 use and emission.